Alright, so here's a basic procedure for balancing equations that works almost all the time. So first of all, some of the ground rules. The idea is that on both sides of the reaction, the number of atoms of each element has to be the same, and the charges, if any, have to be the same. Don't forget, 0 is also a charge. Now, what you can't do, you can't add any other extraneous species or any new atoms or elements because, well, you're changing the reaction. You can't change subscripts, so you can't change the formula because that's, again, changing what the substance is. So basically, all you can do to balance is change coefficients. So this is your tool. All right. So I've got a 5-ish step procedure that helps with this. And I'm going to use the combustion of methanol, whose formula is CH4O, as an example. So like all hydrocarbon combustions, the methanol will combine with oxygen to form carbon dioxide and water. All right, step 0, we're going to balance this element by element. And in this process, once we balance an element, we're not going to have to deal with it again. All right, step 1, look for an element that is present in only one reactant and only one product, and balance that first. So in this case, I'm going to do carbon. So carbon on the reactant side is only present in the methanol, and on the product side, it is only present in the carbon dioxide. And so there's one carbon atom in methanol, there's one carbon atom in the carbon dioxide, so we're good there. Step 2. So now we're going to take an element that is present in one of the species that we just balanced, and only in one other species. So I'm going to use hydrogen as an example. So hydrogen is present on the reactant side only in the methanol, and on the product side present only in the water. And so there are 4 hydrogen atoms in the methanol. We have 2 in a single water molecule, so we need 2 water molecules. So now we have carbon balanced at 1 atom on each side, and we now have hydrogen balanced at 4 atoms on each side. All that's left is oxygen, and keep going. If you can identify more elements like that, do so. Finally, step 3. Wait until the very end to tackle elements that are present in more than one reactant, more than one product. And a corollary of this, 3A, if a species is present as a free element, save that for last. And here we're talking about something like this O2 here. So this substance is composed of just one element, which means you can change its number by virtue of changing the coefficient here without messing up the balance of any of the other elements. So let's figure out what we need to do here. So on the product side, we have 2 and then 2 more. So we have a total of 4 oxygen atoms. On the reactant side, we have 1 oxygen atom coming in from the methanol, and the remaining 3 we need to get in from this O2. So how do you get 3 oxygen atoms from an O2 molecule? Well, you use a fractional coefficient. Now, I know in the past you've probably been told not to do this, and it's actually okay at this intermediate stage. So 3/2 of an O2 molecule will in fact give you 3 oxygen atoms. And at this point, every single element actually is atom balanced. We have 1 carbon on both sides. We have 4 hydrogens and 4 hydrogens, and now we've got 3 plus 1, we've got 4 oxygens and 4 oxygens on both on the reactant and the product side. Everything here is neutral, so the charges are 0 all around, so we're charge balanced as well. The very last step is, if you had to invoke fractional coefficients, is to get rid of them. The way you do this is you multiply every species by the number that gives you the smallest set of integer coefficients. which in this case, 2. So if you multiply everything through by 2, you'll get the smallest set of integers that will give you these ratios. And since you're doing that to every single species, you are not going to disturb the balance that you've already created. So in this case, we're going to have 2 methanols reacting with 3 oxygen atoms to give you 2 carbon dioxide molecules and 4 water molecules. And finally, the 5th step, check just to be sure. Don't forget, this is one of those few problems where you know if you're right or not. Either it's balanced or it isn't. So I just like to make a little table here. So on the reactant side, we have 2 carbon atoms, 8 hydrogen atoms, and 8 oxygen atoms now. And on the product side, we have 2 carbon atoms, 8 hydrogen atoms, and 8 oxygen atoms. So we are in fact balanced. And then maybe the very last thing is to check to make sure that your coefficients are in fact the smallest set of whole integers that would give you this ratio. And you can't reduce this any further because you've got, in this case, a bunch of even numbers and a 3. So this is as reduced as you can get. So that is the balanced equation for the combustion of methanol.